Hello, I'm Andy. This is Maths, the Fun Parts. I realise it's a terrible title in a number of ways. Like, number one, I'm really over-promising. So apologies for that. And number two, it's supposed to be a talk for people who hate maths. So putting maths in the title was a terrible idea. But hopefully there's some people here who have some fear or hatred of maths, but also are open to the possibility that there might be some good that can be found there. And I'm going to try and excite you about some fun things about maths, and I'm going to write code to explain the ideas. So don't worry, there's a lot of code and not that much maths on the slides. So we're going to talk about my favourite bits of maths, which, full disclosure, are groups and graphs. But in order to do groups and graphs, you have to do sets. So we'll struggle through the sets, and then we'll do the groups and the graphs. Not really. Actually, what we're doing is actually kind of fun. So first of all, isn't maths difficult and frustrating? What maths is really is trying to think clearly about particular ideas and then developing language, shared language that we can use to talk clearly, having had those clear thoughts. That's a lot like programming, right? We try to think clearly, and then we develop a language that makes our thoughts more concrete. The fun thing about maths versus programming is that whenever things get too difficult in maths, you can just sort of say that you've done it, and everyone has to believe you. We'll see how that goes. All right, so let's start with sets. Fundamentally, a set is just a group of things. So in lots of bits of maths we need to talk about, I've got these things. Some things are this, some things aren't this, and sets help us think about that. We need to cover it because everything that you talk about in maths almost starts with sets. What's interesting about sets is that, like, the main ideas are quite dull and obvious, and then when you get into it, it's just weird and much more difficult than you thought. So we won't touch on much of that, but we'll mention it. So first thing to say about sets is that you should throw out what you know about sets from programming. The sets we use in programming are derived from the ideas of sets in maths, but actually how we use them in practice, which is like things that often are ordered and sometimes about whether the items inside them are unique, and not really relevant to mathematical sets. So a mathematical set really is just about this one idea. Is a thing a member of a thing, right? So in this case, is this thing, we haven't said what it is, but is X a member of this thing A, where A is a set? So a set is just a thing you can ask, is this a member of it or not? So the way you would do this in code, maybe, my examples are in TypeScript. I got quite a long way through writing my slides in Rust. And I realized that although Rust is good for almost everything, it's really not good for writing simple examples for slides. I ended up with a lot of diagonal brackets. So my examples are in TypeScript, which gives us a type system, but isn't too picky about stuff either. This is trying to communicate the concept of a set. A set is just a thing that might contain something. And in particular, you can pass in something of type any in my example. You can ask this question about anything. So we want to decide for each thing, is it a member of this set? So we can ask, and if X is a member, then our contains method is going to return true. So if you're not familiar with this expect stuff, this is the way you write assertions in Jest. For better or worse. For slides, probably for worse. So. Okay, so here's your first bit of maths. So A is a set, X is a thing, which might be a member of the set, and we use this symbol, it means is a member of. So when you see that, you can read that as is a member of. When you see that, you can read that as is not a member of. With me so far? So I meant to say at the beginning, I would like this room to be a safe space. I don't get to say whether rooms are safe spaces or not. That will be up to you to judge. But I totally get looking at a page of code or a page of maths or whatever and just feeling blind, right? And just not understanding it. So please stick your hand up if I'm skipping past something or something like that. But yeah, here's your first bit of maths. Is a member of. Just read it as is a member of. Most of the mathematical notation we're going to look at, you can basically translate it into English. And once you've learned the conventions for the way that English works, it makes sense. But the missing part is often that second bit of the conventions for the way that English works. Okay, so here's an example of a class that implements our interface. This is a class called set123. It has the contains method, which is the only thing I said you need to have to be a set. And this returns true if you pass in a 1, 2, or a 3, and it returns false otherwise. So this is the set of the numbers 1, 2, and 3. There's no array inside this set containing those numbers, but from a sort of mathematical point of view, this is identical to something that did have an array of 1, 2, and 3 in it, something like that. So there's your example of a set. Here's some unit tests, just to be sure. So set 1, 2, 3 contains 1 and 3, doesn't contain 0 and 4. With me so far? Okay, so I won't show you the implementation because I'm sure you could do it, but here's an example of another set I wrote, which takes in an array, and then the things in that array are members of that set. Make sense? Notice that you can ask about things that are different types of things. So you can ask about 3. 3 is not a member of this set. You can also ask about another set. Is that a member of this set? No. Okay, so that was sets. And things you can do with sets is you can form intersections of sets. So here's some code to explain what an intersection is. So this is a class which implements set, and in order to construct it, you pass in 2 sets, and then it has a contains method because that's how you be a set, and it decides that this thing that you've passed in is in the set if the first set contains it and the second set contains it. So an intersection is the things in the 2 sets that are in both. And this is how we write that. So, yeah, if you're already becoming blind from the mathematical symbols,
it gets worse.
Then I guess all I can say is take a deep breath. This just means the intersection of A and B, and we've just looked at the definition.
It's just a croquet.
Yes.
Yeah, it's just a croquet.
When the 2 balls hit.
Yeah, so how to remember, the way I remember that this way up is intersection is because the other way up is easy to remember. We'll get to that in a minute. Okay, so we'll do a little bit more notation. So this is repeating what I just said. So if x is in A and x is in B, then x is in the intersection of A and B. Okay, that's just sort of the way mathematical sentences work. And the only change I've made here, weirdly, the fonts changed because most of my SVGs, I converted them to not text so that they wouldn't go wrong, and some of them I forgot. So I don't know which one this is, but so I replaced the word then with this arrow. So this arrow means implies, or it means maybe then. It means if the thing on the left is true, then the thing on the right is true. But actually, in this case and in some of the other cases we're going to look at, it's more than just if the thing on the left is true, then the thing on the right is true. It's also if the thing on the right is true, then the thing on the left is true. So in this case, this is like a definition, so it's kind of obvious that they're the opposite of each other. They both imply each other. But in some cases, that's not obvious. So when that little arrow changes from one direction to two directions, sometimes something quite special is happening. Okay, so in summary, if X is in A and it's in B, then it's in A intersection B, and also vice versa. Yes?
Couldn't you replace the English word "and" with some fancy symbol?
Couldn't I have replaced the word "and" with something fancy and mathematical? Yeah, and I mean, yeah, and I could have just put a comma maybe, and sometimes commas carry all kinds of meanings. So we'll get to a slide later where I wish there was a mathematical symbol, and I've just written a comma. So maybe someone can help. But in this case, yeah, "and" is the clearest way I could think of. Okay, so we talked about intersection. Now let's talk about union. So union is combining two sets together in a different way. So again, this is a class that implements set, and it takes in two sets, and it has a contains method because it's a set, and it returns true if either element is in set 1 or element is in set 2. So what that means is that you've now got a set which has got all the things that were in both, that were in either. And the way we write this, and this is why I find it easy to understand, is because this symbol looks like a U and it's a union. If you can't remember whether the word union means, which the two words mean, then this doesn't help you. But it kind of pulls them together instead of crossing them over. Maybe that's how I really think about it. So nothing new there. That's just how we write union of A and B. And this is the full kind of mathematical sentence or definition. And the change here is that the word "and" became the word "or." So if X is in A or it's in B, then it's in the union of A and B. And also, if it's in the union of A and B, then it's either in A or it's in B, or both. If we write "or" like this, we normally mean either or. I mean and or. Okay, so let's move on to another idea, which is the idea of a subset. So a subset is a set with a particular property in relation to another set. So this is a method on a class that is some kind of set, which will tell you whether it's a subset, whether this class is a subset of this other class. And the way it does it is it loops through all the elements in this set, and if one of our elements is not in the other set, then we're not a subset, and therefore if all of our elements are in the other set, we're a subset. So a subset is a set that has all its elements are also members of the other set. But if you are eagle-eyed, you'll notice that I did something that we're not allowed to do, which is I looped through all the elements of this set. But that won't work for the definition of set that we've got. We've only got one method on a set, which is contains. So we're going to need another slight modification to our code. We're going to need something that's like an iterable set, which in this case I've defined as being a set that's also iterable. And yeah, so we've got this, don't worry about the TypeScript, I don't understand it. So the way that works in maths is there's an interesting difference between being iterable and this thing in maths called for all. So when you see this upside down A, it's not a font problem, it means for all, which means like the thing I'm about to say has to work for all the things. You'll see. So for all. So if we want to say that A is a subset of B, notice that this A is capital because these are both sets now. If we want to say A is a subset of B, and this is the symbol for is a subset of, we're reusing the U shape for a lot of things, aren't we? Then we write the definition like this. If for all X in A, X is in B, then A is a subset of B. So I'll give you a moment for that. Because there's like two sets of if-thens happening in this one sentence. So basically, given that for all x that are in A, that x is also in B, then A is a subset of B, and vice versa. If A is a subset of B, then for any x you give me in A, it's going to be a member of B. So there's really maybe another little arrow here instead of this comma. But this is the normal way that I've seen this written. And again, the arrow goes both ways. So, with me on this. It's just the same as the code we saw, except in maths, instead of in programming, if you want to be able to say for all things, you have to be able to loop through all the things. In maths, you just say, well, for all the things. Yes?
In maths, it works for uncountably infinite sets too.
Yes, and we'll get to that. Yeah, so in theory, it can work for things that don't make any sense in a programming context. You just put for all, and then someone else. The universe does the iteration for you. Okay, so let's think about some infinite sets. So here's another thing that implements sets. There's another set. And it's called evens because it contains anything which is a number, and that number is even. Again, try not to worry about the beautiful world of JavaScript and TypeScript that I live in, and just take the sense of this code. This is how you write this in maths. We've got a set called evens, and anything x is in evens if, ignore this for a second, and x modulo 2 equals 0, so if it's even. All this means that this might look a bit scary, but all this means is x is an integer. Z is the set of all integers. I won't go into that anymore. So now let's think about this a little bit more. So we wrote for all x in evens. How would we do that in code? We could sort of implement iterator for evens using nice yield syntax. So what we'd do is we'd yield 0, then we'd yield 2, then we'd yield -2, then 4, then -4, and so on. We could get through all of the evens, except, of course, that method will never end. But in maths, that doesn't really matter. Okay, so we saw very briefly earlier that sets can also contain sets. So let's define a new class which implements sets, so a new set, and let's call it all sets. And then we'll do some eval because you can't really check types properly in TypeScript. Let's imagine that this comment here was me checking that the thing you passed in was a set. That basically contains returns true if you give it a set, and returns false if you don't give it a set. So let's test that a bit. So the empty set is a member of all sets, and the set we saw earlier, set 1, 2, 3, is a member of all sets. By the way, the empty set, which we haven't actually seen, that returns false when you ask if something's in it. Very, very important in maths, probably not much use in programming. So just some notes about that. So the set evens is a member of the set all sets. Have I got a code example? Yeah. And what's more, the set all sets is a member of all sets. Like so. And in maths, you can just do that. And there's a shaking head because this whole thing is slightly built on a lie. Because since about 1970, set theory has been taught using a different set of axioms from what I've given you, because this set of axioms doesn't work. And part of the reason it doesn't work is because the set of all sets being a member or not a member of the set of sets that are not members of themselves is a real problem. And we'll move straight on from that to groups. Okay, so that was set. So that gives us a bit of vocabulary for how to do maths. And I've given you the sort of working definitions that are in my head for how sets work. And real set theory is more full of details. Okay. So groups are about thinking about algebra in a more abstract way. So in algebra, groups are about thinking about like arithmetic and that type of stuff in a more abstract way. So when we do maths, we add up numbers, we get answers. And when we do algebra, we replace the numbers with letters, so they could be anything within some constraints. But that leaves a sort of elephant in the room, right? Like, we've replaced most of the symbols in this equation. But what about the plus symbol? Why can't we replace that with something? Well, you can. So in this presentation, I'm using this weird symbol so that you know that it's not like a plus. Quite often in group theory, people will use a star, but we programmers use a star for something else. Or just a plus sometimes, which I find really confusing. But yeah, the point of group theory is taking this operation and saying, what happens if that is an abstract idea instead of something that's already known about? So here is a definition of a group. So a group is a set and an operation, and we'll get on to identity in a minute. So a set is like the things that can get added up or combined together, and the operation is how you combine them together. But it's not something that conforms to this interface. That isn't enough to say that this is a group. It also needs to follow some rules. So here's a way we might say this in more mathematical terms. A group is made up of a set and an operation, which we will call dot. I'm going to call that dot. But they follow some rules. By the way, in case you were missing it, this is the fun bit now, right? Okay. So here's an example of a group. This group is called plus mod 5. And I'm showing you the operation that you can do on the members of this group. When you get two numbers in, you add them up and take the answer modulo 5. And we'll show that that is a group. So just an example of how that's working. We make the group and then we do the operation. And when you add up 1 and 2, you get 3. But when you add up 4 and 3, you get 2. Now, does that slide make sense? So 4 plus 3 is 7, modulo 5, that's 2. So our binary operation, which we're calling dot, is just a way of combining together two members of the set that's the other part of the group. So this is what plus mod 5 looks like in sort of mathematical terms. It's a set of these numbers, and it's an operation called plus modulo 5. But it needs to follow some rules. So the first rule is one that in some contexts feels obvious, but in the case of plus modulo 5, it's kind of important and interesting. If we were working with something that wasn't closed, perhaps we were using the numbers 0 to 4 and then just ordinary plus with them, then we could end up with an answer from one of our operations that is not a member of the original set. So if we added 1 to 5 and got 6, but 1 to 4 and got 5, and we didn't have 5 in the original set, things are going to get difficult for us if we end up outside of the set we started off with. So that's what closure means. So the way that's written in mathematical terms is, for all A and B that are members of our set, when we combine them together, the answer is a member of our set. Does that make sense? So plus mod 5 is a group, but in order for us to validate this in code, we're going to have to say that it's an iterable group, similar to what we did with sets. Now we can loop through the members of our group. So we can express the rule of closure in code by saying get me some elements that are inside the group, X and Y, combine them together with the group operation to get Z, then every time you do that, that Z should be also a member of the set. Make sense? Closed it just means like this operation kind of works for this set. We don't end up with something that we don't know what to do with because it wasn't a member of the set. So is plus mod 5 closed? Yes, because every time you add up those numbers and then do modulo 5, you get another one of those numbers. This is just an example, not a proof, by the way. Okay, rule number 2. There must be an identity. So here's the way an identity works. So here is where we get hold of the identity. We loop through all the members of the group, and well, really it's the members of the set that is part of the group. And then when we do the operation of combining identity with X, the answer is X. And also if we do it in the opposite order, when you combine them together, the answer is X. So the rule says there must be a member of the set which is an identity, which means that for all of these X's in G, if you combine it together with the identity, you get back the X. So in order to express this in mathematical terms, we need this symbol, which again looks like someone's just like mirrored some stuff in your text editor. This is pronounced there exists. So we can use it in a sentence like this. The rule for identity is that there exists an I, so there exists some element I in our set such that, by the way, if you see S dot T dot in maths, it just means such that, which in itself, what does that mean? And it kind of means, like I've established this thing I, and the following stuff works for it, right? So there exists an I in the set such that for all A in the set, so everything else in the set, or in fact itself as well, if I combine A with I get A, and if I combine I with A, I get A. So I'm seeing a look of confusion there. So I'll give you a minute, and then if you've got a question, you can ask it. So you might be wondering, why are we doing both orders of A and I? And if you are, it's because sometimes this dot operator is not the same backwards as forwards. In the case we've looked at so far, it was. So that might be why it's confusing. But yeah, so basically there must exist an I that has this property that for all the A's in the set, you get back A when you put in A with I. One of the nice things about maths is that you don't necessarily have to find this I. It's enough to just show that there must be one. Sometimes that's really useful, and some people hate that. So does plus mod 5 have an identity? Yes, you might have been able to guess it. It's called 0. When you add 0 on either side to any of the members of plus mod 5, you get back the same answer. Okay, so that was identity. So any questions on identity? Yes.
The reason I'm frowning is not because I don't follow it, but because I don't see why you'd care.
Why would you care whether there's an identity? Yeah. Okay, so I'm really not explaining why you would care about any of this, because it just seems so beautiful. Why would you? So I guess the point of groups, why you would care about this particular set of rules, is that you want to come up with a definition of arithmetic that in some sense behaves well for some task that you're doing. So if you don't have an identity, in particular you can't have inverses, and if you don't have inverses, there's some types of sums you can't do and things like that. So we're going to get on to inverses.
Starting to care.
So let's talk about inverses. So here's a little snippet of code that doesn't show you anything yet. But the rule of inverses is that every element of a group must have an inverse. So let's have a look at what the function has inverse does. It takes in the element and the group. We could have made this a method on the group or something. So having an inverse means there exists some element y such that if I combine E with y, I get back the identity in both orders again. But that's the fundamental thing. So an inverse is a thing that takes you back to 0 or whatever your identity is. So in the whole set of integers, the inverse of 2 would be -2. Of course, in plus mod 5, you need to do a little bit more in your head to find the inverses. So now, I know these sentences are now getting quite long, but you have all the tools already to understand them. And it's the same stuff that we just looked at. For all elements in S, so for all elements in our set that forms our group, there exists another element, or maybe the same element, such that when I combine them together, I get back I, and also the other way around. So does that sentence work for you?
Is it ever the case that it doesn't work the other way around? Is it necessary to have x dot y and y dot x?
Yeah, so is it necessary to have x dot y and also y dot x? Yes, it is, but I haven't given you any evidence yet that it is. So we will come to some groups where the two answers are different. So far, we haven't seen any.
I get that it would be the case because like division it does work for for the identity though. Does having the identity does x dot y equaling the identity not give you y dot x equaling the identity?
Okay, that's a good question. So the question is are there cases where the identity, where there's an identity that only works on the left and not on the right? There definitely are. I can't remember the details, but that would not be a group.
Yeah.
So it would be some other type of object. There are cases where you have like left identities, I think. But we don't have to think about them because we're doing groups. Okay, so inverses in plus mod 5. So the inverse of 2 is 3, which is almost the same as saying -2 mod 5 is 3. Maybe? Don't know. This is how I'm writing plus mod 5, by the way. I didn't mention that. Later, another nice thing about maths is that you can write things how you want. So I write this, and then later I get bored because that's just too much writing. So I get rid of I just say plus 5. You can do that in maths. Okay, there's another rule which is more boring, which is that if you've got 3 things that are members of S, it doesn't matter what order you do your bracketing. Again, this is a property that is not true of all arithmetic systems, but is handy to have. And the S plus mod 5 is associative. We can build on the fact that we know that plus is associative. There's also another optional rule you can have, so you don't need this one, which is called commutative, which is a very, very posh word for backwardsiness. X and y and x, they're the same. So when would you not have commutativity? So yes, plus mod 5 does have commutative property, so it's an abelian group if you really want to sound clever. So let's have an example of something that doesn't use numbers, that is a non-commutative group. So we're going to go a long way away from numbers. So you're going to need to reset your brain, maybe. So this group is called D6. Because it has 6 members. And D is like the symmetries group. Why is it D? I don't know. Right, okay, thanks. This is a group of things you can do to a triangle, and it still looks the same after you've done them. So if you ignore the A, B, and C, they were just put there for us to figure out what's going on, and just think what rotations and flips and things can you do to that triangle, and it still looks like a triangle, equilateral triangle. So here's all the things you can do. So one of the things you can do, of course, is do nothing. This is a very mathematical way of thinking. And then the other things you can do is rotate it once, rotate it twice, which is the same as rotating it backwards once, You can flip it on its horizontal axis, you can flip it on this diagonal axis, or you can flip it on this diagonal axis. Do you believe me that those are the things you can do to a triangle? It still looks like a triangle. Yes?
Scale.
Yeah, you can scale it, but that doesn't look the same according to my rules. So it has to look the same and be the same size. For this,
only works for equilateral
for this group.
triangles.
Yeah, only an equilateral triangle, yeah. So, yeah, the triangle here is just a tool for our thinking. Okay, so those are the things you can do to a group, yeah.
Is there, you mentioned that rotation of 240 is the same as going the other way, but it's 2 in one direction versus 1 in the other direction. Does that make a difference? Do we care?
So, yeah, the question is, rotating backwards by 1 is the same as rotating forwards by 2. Do we care that whether those are the same thing or not? Is that the question?
I mean, the outcome is the same, but how to get there isn't necessarily.
Yeah, so all we care about is that the letters end up in the same place. That's going to be our definition of equals. So the bit I've skimmed over, actually, in this whole thing is that the other symbol in our equation, A dot B equals C, is the equals. And for numbers, we have a very clear, intuitive definition of what equals is, and you're doing very well to pick up that actually in this case, and gentlemen in the back as well, we actually need to be a lot more clear about what we mean by equals before we can really get anywhere. But yeah, in this case, we mean the letters are in the same place. And not the same way up, right? I've rotated the letters because it kind of helped my brain, but yeah. So these are just ways that you can flip or rotate stuff. And there are rules in this system. So just like 1 plus 2 equals 3, rotate 120 degrees and then horizontally flip equals doing one of those other flips. And because we've all convinced ourselves that those 6 are the only things you can do to a triangle, we know that this group is closed. So obviously combining them together must result in another member of this group, right? Because that's what being closed is. So I've skipped over the fact that this plus here means do one, then do the other. That's our group operation. And here's another one. So we can horizontally flip and then rotate, and we get something equivalent to the other flip. Yes?
Those are not commutative, correct?
That's correct. So exactly my point in this, that having these 2 slides, thank you, is they're not commutative. So you can rotate and then horizontally flip, and you get TL flip, or you can flip and then rotate, same rotation, and you get TR flip. So the whole point of this group, including this group, is this is a group, but it's not commutative. It doesn't follow that rule that A dot B equals B dot A. But it's still a group because it follows the other rules. And it's one of the simplest commutative groups. And here's another one. Sorry, non-commutative groups. Here's another non-commutative group. You can represent all the positions of a Rubik's Cube as a group. They follow the rules. So I need to be clear about what I mean by that. So the members of this group are all the ways of rotating, doing multiple rotations of, multiple valid Rubik's Cube moves. So not just one move from the starting position, but any number of moves. So exactly the same as we're combining together rotations of triangles. Here we're combining together turn that, then turn that, then turn that. And you can kind of intuitively feel that it's closed because you've still got a Rubik's Cube at the end of your every turn. There are inverses because you can always do the same thing backwards. It is associative, just believe me. But it's not commutative. And any guesses at the number of members in this group?
16 trillion.
We have a guess of 16 trillion. The answer is, I think it's 43. I think that is quintillion members.
43 many.
43, lots and lots and lots and lots.
It's a the counting. So we're doing computers is 0, 1, 2, and then.
Yeah, in that case, it has many members, But yeah, it's a group. And thinking of it as a group can be helpful for, probably not for solving it, but for thinking about it, thinking clearly about it. Okay, there are also infinite groups. So this R means the real numbers, which are a deeply mysterious set of all the numbers that you normally deal with and didn't realise were so mysterious. And that means times, so timesing together real numbers. It's a group.
You have to exclude 0.
Excluding 0, thank you. Yeah, so it doesn't work if you include 0. Sorry, so this is wrong. If you include 0, you can't inverse.
Yeah.
So, yeah, you can't get back from 0 to 1. 1 is the, yeah, so well, I shouldn't have even brought this group up. The identity in this group is 1, not 0. 0 is not in this, so this is incorrect. It should say R with 0 missing.
I thought what you were demonstrating is real numbers are hard.
Yeah. Thank you.
Efficiently demonstrated.
Yeah, that R is just so complicated that I shouldn't have put it on the slide. Another famous group is the elliptic curve group, which you might have heard of from elliptic curve cryptography, which is related to group theory, right? So that cryptographic method uses the elliptic curve group. So an elliptic curve, I looked this up. It's a curve that looks kind of like this, or like this, drawn in a 2D plane. And I think it follows some other rules. And the group operation in this group is if you've got a P and a Q that are in the group, then the other line on the other point that crosses that line in a straight line is the inverse of adding up those P and Q. All right? So yeah, you've got P and Q and you're looking for R. So what you do is draw the line from P to Q, and where it crosses the line, you've got R, and then the actual answer to P plus Q, or P dot Q, is minus that thing, which will be in the opposite corner, over here somewhere. I don't know what that means. So let's quickly move on to graphs.
Before you missed that. You missed associativity.
I skipped quickly over associativity. Because it's a bit boring.
Yes.
But it was there. Okay, graphs. So that was groups, so now we move on to something completely different, a little bit more visual if the less visual stuff was getting you down. So a graph is a collection of dots and lines. And sometimes people introduce you to a bit of maths. They say, oh, it's just dots and lines. And actually it's not. But in this case, it actually is just dots and lines. Right? And the rest of it is just on top of that, which actually means it's quite difficult to do in code. So in order to sound mathematical, we don't call them dots and lines. We call them vertices and edges. By the way, the word graph here has nothing to do with the colloquial use of the word graph, which we would sometimes call a chart, right? So it's not bar charts or anything like that. It's dots and lines, but we call them vertices and edges so that people don't think we're just messing about with dots and lines. So this is a graph because it is some dots and some lines. And here's how we might write some code that represents a graph. I'm actually only going to talk about finite graphs here because I know nothing about infinite graphs.
Finite, they don't stop.
They're like finite, but they don't stop. And yeah, I don't know anything about them, so I'm not going to talk about them. It's really difficult to write code that represents graphs in a nice way because, yes.
Just to help out that, look at Cypher and the way it does graphs.
Look at Cypher.
In notation, it's beautiful for the graph syntax.
Is that a Python library?
No, Cypher is a query language for Neo4j, which is a graph database.
Cypher, the query language for Neo4j, apparently really good. So look at the implementation of Cypher, are you saying? Or?
Yes,
yes,
for representing graphs in text like that.
Brilliant, thank you. Yeah, so it's really hard because a graph consists of vertices and edges, and the edges are kind of references to the vertices, right? So you've already got like a pointer in there somewhere, so it's very painful. So just to be clear, when I say it's dots and lines or vertices and edges, what I mean is these are the dots, they exist, and in lots of graphs all they do is exist. And a line, an edge is just the fact that there is a connection between them, right? It's not, you can't like draw a bendy line or something like that. You could have multiple connections between them, but it's just the fact that they're connected, which is why we can represent them here as, this is like templated on the type of the vertex, but basically we're saying the vertices is just a list of things, like they could be, say, numbers, 1, 2, 3, 4, or letters, and then the edges are basically saying this thing is connected to that thing. So it's an array of pairs. That's a terrible way to represent it, but all ways of representing graphs are terrible. So here's an example of a graph called K3, implements finite graph, and I've specified the type here. The nodes, the vertices are strings. By the way, if I say nodes when I meant vertices, that's because sometimes I say nodes when I mean vertices. They seem to be used interchangeably sometimes. So the vertices of this graph are just the strings A, B, and C. And then the connections between them are A is connected to B, B is connected to C, and A is connected to C. And in this particular case that we're looking at, the direction doesn't matter. We'll mention very briefly later situations where the direction can matter. And we could have 2 copies of A is connected to B, right? But I won't talk much about that. So that's your example of a graph. So with me so far, there are things, like vertices are things, and then those things can be connected or not connected, or connected multiple times. And then there's a concept about graphs. You can say a graph is either connected or not connected. If it's connected, then from any point in the graph, you can somehow jump through edges and get to every other point in the graph. And that's true of all points in the graph. And a disconnected graph is one where that's not the case. With me? Mm-hmm. Okay, so then writing the code. So the code bits now get quite nasty, and the diagrams are much nicer. So this is a really good demonstration of how maths is really great, right? So to figure out whether a graph is connected, here's the code I wrote. So first of all, we pick a vertex and put it into a list called found. Then we walk all the paths from that vertex, which I think I didn't put the code of because it got too long. And then for every element in the path, if it's not in the found list, add it to the found list. If the found list is as long as all the vertices, then return true. Otherwise, if you get to the end, you didn't find all the vertices. So walking all the paths is just the kind of annoying code that I'd probably have a bug in if I did put it up. Okay, so another concept, yeah.
I'm still
Yeah.
bothering about what's the difference between a disconnected graph and 2 graphs?
What's the difference between a disconnected graph and 2 graphs?
If the 2 graphs were also disconnected, then the question ought to be what's the difference between that and 4 graphs? And if each of those were then disconnected, then it would be what's the difference between that and 8 graphs?
Hang on, turtles. I see turtles.
It's a worm cap. I mean, you could say that's 2 connected graphs because that's 1 disconnected graph. It depends on pros or posts.
So basically, a graph is whatever you want, and it can be either connected or disconnected. So if you wanted to have 2 graphs, you could have 2 graphs, and they would be, in this case, they would be connected graphs, each the separate ones. But
I think an example there could make it clear why, because usually when you use disconnected graphs, it's because they live in the same system. So if your vertices would represent cities, and your edges would represent rows, if there's no road between 2 countries because there's a sea between them, that's a natural disconnect, but they're in the same row sort of graph. So
that's a good example, yeah. So the example is, if these were represented cities with roads between them, then the reason you talk about whether the graph is disconnected or connected is because it matters to you whether you can drive from here to here because they're both cities. Maybe you should use the other graph of like
Does that also
flights.
mean that a dot on its own is a single graph?
If you say it is, yeah. So a graph can. So the question was, can a dot on its own be a graph? So yeah, any collection of dots and edges can be a graph, including no edges and no dots.
Is a single dot a connected graph or a disconnected graph?
Is a single dot a connected graph or a disconnected graph? Well, I believe that this function will give you the correct answer.
Or it's a bug.
You
Yeah.
can have an edge that goes from one vertex to itself.
You certainly can have an edge that can go from both vertex to itself, but a single vertex with no edges is a connected graph. Yeah.
Where this function would return false, right?
So it's fine.
For that case.
So the one view is not right.
Oh gosh, yeah. You're right. Yeah, there is a bug in my function.
Sorry.
I so confidently said that I thought it gave you the right answer. Well, there's a missing test case from my test suite. It's all on. It's all up on codeberg.org. So you feel free to make a pull request to fix it. Did you have an additional question, or was it just to point out the bug? Yeah, thank you. Yeah. Yeah, I'm very sorry, but I'm sure my maths is correct. It takes like 20 years of peer review for people to find the bugs in maths papers, so it's much easier. Okay, we need another concept, which is the degree of a vertex. So the degree of a vertex is the number of edges that connect to it. Simple as that. And here's a function, which might or might not calculate the correct degree of a vertex. Given a vertex and a graph, go through all the edges in the graph, and if either the from or the to, oh gosh, I found a bug already.
Yeah. Self-connected.
If the from or the to match that vertex, then we add one to the number, but of course if they both do, we need to add two. So another bug, and another pull request incoming before the end of the talk, I hope. Okay, so fortunately, this is a talk about maths, not Andy's coding ability. Okay, so I want to introduce you to an idea to do with graphs called an Eulerian circuit. So an Eulerian circuit is named after Euler, and famously there was, he talked about the bridges in Königsberg and wanted to work out, is it possible to walk around this graph, visiting every edge once and only once, and ending up back where you started. So the bridges in Königsberg were modelled as the bridges were edges and the bits of land were vertices. So here's a picture of that with a solution, right? So yes, there is an Eulerian circuit to get around here. Visiting every edge. You can visit vertices as many times as you want. So can you make an Eulerian circuit around this graph? I can see nods. Yes, so you can do like a figure of 8 if you like. And we're visiting this vertex twice, but that's fine. You're allowed to do that. It's just the edges. So it's the bridges that you want to only cross once. Can you make an Eulerian circuit around this graph? No. No.
One on the left or one?
No. So it's easy to say that a disconnected graph has no Eulerian circuit. And in a later slide, you'll see that I forgot to mention that because it's assumed from this slide, right? So no, you can't make an Eulerian circuit around here. What about this graph? Can you make an Eulerian circuit around this graph? I see some nods, I hear some no's. There's some disagreement, So you can do this, right? You can start here and end up here, but that's not a circuit. So that is an Eulerian trail. So well done. You did find an Eulerian trail. You did not find an Eulerian circuit. So I want to tell you, so that was just Eulerian circuits. So now I want to tell you some insight. So we're going to do some maths and learn about graphs that have Eulerian circuits. So if a graph has an Eulerian circuit, then for all of its vertices, the degree of that vertex is even. And I've said obviously question mark, because this is one of those things where your lecturer in your maths lecture will probably say obviously, and then you need to go away for a few days and figure it out. Yes?
That compile symbol in the middle, are you going to explain that, or did I miss it before?
You did miss it,
okay.
But it means if this is true, then this is true, and it goes in one direction, and that's critical. So keep an eye on that symbol. So obviously, the degree of all the vertices are even, so I'm going to try and convince you of that using classic graph theory proof technique, which is showing you a diagram and going, it's obvious. So if we think in terms of vertices, even though we kind of already got in the habit of thinking vertices are not very important for this problem, but it turns out they are, if we think in terms of vertices, in order to get back to where you started, every time you enter a vertex, you must leave it. So there's always going to be an even number of edges, given that you're going to visit all the edges. So have I convinced you by pointing and saying it's obvious that the degree of the vertex will be even? Some nods, some non-committal faces. That's all I've got though, so.
I like your engineering proof.
Okay, so we already had, if a graph has an Eulerian circuit, then, pointing to the right, for all vertices, the degree of that vertex is even. And now we know it's obvious. But it is also true, and not obvious, that the opposite implication is also true. So it turns out if you have a connected graph with an Eulerian circuit, if you have a connected graph all of whose vertices have an even degree, then you will be able to find an Eulerian circuit. But I'm definitely not going to prove it for you. It was suggested by Euler, but not proved. It was proved by Karl Heyerholzer a long time later. It's not that easy. I mean, these days it's easy enough that you would learn this in your first year maths degree, but it's not easy enough for me to remember or explain how you do it. But it's quite surprising, isn't it? Yes.
I have a maths degree and I hadn't read any of the years.
Oh, apparently not all maths degrees.
I didn't go to all the lectures though.
It could have been one of the lectures you didn't go to. So it's quite surprising, I would say. And it's incredibly useful. It's not as useful as being able to say, if you give me this graph with this property, I will give you a circuit. That would be really useful. And maybe there are proofs that do that, but there certainly will be proofs that don't do that, but still demonstrate it. So it's another nice thing about maths, right? Just because you've proved that something is possible, you don't have to actually do it. But yeah, you will. What this proves is that if you look long enough in that graph that you've been given, you'll find one, which is cool, right? And that, you could imagine that being quite useful.
Yes, your search will hold.
Yeah, your search will.
Very long time, but it'll hold.
Yeah, your search will hold, and yeah, you will find. It tells you what the outcome of your search. Yeah. I accidentally told you something useful. I apologise. Okay, so I'm going to move on from undirected graphs to directed graphs. So directed graphs are dots and lines, but the lines have arrows on them. So what that means is that there's an edge from here to here, and there's not an edge from here to here. That's the phrase we use, right? So like quite often that'll be because you want to be able to traverse from here to here or something like that. But in terms of what it really is in graph theory, it's just a line with an arrow on. And it's not the same thing as a line with an arrow pointing the other way. And yes, you can have both directions, and you can think of an undirected graph for some problems as like every time there was one line, you just replace that with these two lines going both directions. And for some problems, that's like a valid transformation. So here's an example of a directed graph. And now I'm going to talk to you about why this is useful. There is a thing called Secret Santa, which is a game where you have some people, they're the vertices, and everyone is going to give someone a present, everyone's going to receive a present. And on first glance, it's as simple as that. But in practice, you certainly don't want people to give a present to themselves. You probably don't want pairs of people swapping presents, because then that can get difficult. You probably don't want to buy for your partner if your partner's in the group, or someone else with a close relationship. And additionally, you want to make absolutely sure X doesn't buy for Y, because X is a terrible person. So in practice, what you end up with is this group of people, and we're going to represent can buy for as an arrow pointing from A to B. And you end up with a directed graph. So this is not a graph of who is giving to whom. This is a graph of who is allowed to give to whom. And the fundamental problem in Secret Santa is to make a graph of who is actually giving to whom. Now, obviously, there's some other stuff, like you need Fran here to do some randomness, otherwise it's going to get very dull next year. But yeah, fundamentally, you need to find some subset of these edges where everyone gets a present and everyone buys a present, and it follows our rules. Now, that's not exactly the same thing as what I've said here, but in order to make it more fun for myself, I decided that Secret Santa was going to find a circuit in a directed graph that visits all vertices.
Only a programmer could write a program to do Secret Santa. Most normal people just go give the presents.
Yeah, so the comment is that only a programmer would do this. I mean, we're here for fun. This is how I make my life fun. So actually, like, what you could do is find a lot of circuits of length longer than 2 if you want that rule. And in order to solve this problem, I wanted to do, whenever I've done Secret Santa for my friends by hand, which I've done quite a lot of times before I got around to this, I always wanted to make it a full circuit. It just feels better. So let's do that. So we're not solving the general Secret Santa problem. We're solving the Hamiltonian circuit problem. So Secret Santa can be solved by finding a Hamiltonian circuit in the directed graph of who can buy for whom. A Hamiltonian circuit is a circuit that visits all nodes and ends up in the same place. All vertices, sorry. So don't confuse this with an Eulerian circuit, which visits all edges. With me?
Yep.
Visit all nodes. Turns out it's much harder. So Eulerian circuits are basically solved, right? You just count the degree and then you know you can find one. And then finding one, not that bad. Yeah, exactly. Exercise for the reader. So you can visit santacircles.artificialworlds.net, and you too can have your Secret Santa circles calculated for you using my code. And you've seen my code now, so it's written in Rust though, so I think it's guaranteed to be correct. Yeah, that should still be up at Christmas. It worked for me last year. I can't guarantee it works. And in order to do this, I did something really fun, which was I made a pull request against PetGraph, which is one of the leading Rust libraries for graph theory stuff, implementing an algorithm by Frank Rubin from 1974, because I believe the state of the art of finding Hamiltonian circuits is from 1974. I could be wrong. I'd be really interested if you found someone doing it better. But yeah, I felt so much like a mathematician when I was doing this. I printed out this paper, which looks like this. It's all wobbly because it's typeset on, I don't know what, it was photocopied multiple times. And then I drew on it in pen, like a proper mathematician, in order to figure out how to implement this thing. And my pull request is still a pull request because in the last comment on it, I said, I fixed the bug, but it's made me think there are probably other bugs like this. And weirdly, they haven't merged it into... Anyway, it does find Hamiltonian circuits. It seems to work. As I said, it worked at Christmas. Okay, so I'm going to very, very briefly give you the very high-level overview of what Rubin does to find Hamiltonian circuits. So it's nothing like as nice as counting the degrees of the vertices. In fact, it's been proved, I think, that you can't do better than like exploring the whole graph to find out whether there's a Hamiltonian circuit or not. But where exploring the whole graph is where is what we can refine to make this better or not. So what Rubin did was made that a bit quicker, but fundamentally still a difficult problem. So essentially what he does is eliminates a lot of impossible stuff as he goes. So what you have is you have a kind of working set of a kind of a path that you're currently trying out to see whether it's a Hamiltonian circuit. So you've picked some starting point, and you've got some edges that you've already gone down, which I'm going to call definite edges. And then based on that thing, which is not, by the way, not guaranteed to be the correct answer, it's just the thing you're currently exploring, you start exploring this thing and saying, okay, these three edges are definitely in. Now, what implications does that have? So, for example, one of his rules is, if you've got an edge like this red one that leaves this vertex, then these other edges that also leave this vertex must be not in the path, right? If this one's in the circuit, then these two must be not in the circuit because we've revisited that vertex. So it's just rules like that, and it massively cuts down the search path. So here's another rule, which is if I'm following all my rules and making up this definite path, if I end up in a vertex that I've already entered, if I'm entering a vertex I've already entered, this path must be wrong, and I'll move on to the next one. So there's a load of rules like that. You kind of prune out all the edges that you know are not needed, and it means that your very complex search is still very complex, but smaller. Yes?
What's a definite edge?
So a definite edge is just the word that I'm using for the current candidates. Like I'm making up a path to see whether it's Hamiltonian or not, and the edges that I'm currently considering part of the thing I'm looking at, I'm calling definite edges. I'm not sure what he calls them.
Member of your candidate set.
Exactly.
Okay.
So in this case, like we've hit a problem. So
It's a good word, by the way. Definite edge.
sounds nice. Okay, so that was. So oh, thank you. So that was graphs. So we've done sets, we've done groups, we've done graphs. Any questions about that stuff? All right. So how long have we got? I'm going to stop in a minute so there's time for questions and time for you to find the next thing. So I just want to briefly mention some stuff that I didn't talk about. So we mentioned infinite sets, like the even numbers, right? And I actually gave you a way of counting all the even numbers. Like it never ends. If you go 0, 2, -2, 4, -4, you eventually count all of them if you count for long enough. And actually, there's a way of counting fractions, which is maybe quite surprising. If you try and figure it out, it's quite difficult. But there's a way of counting all fractions, A divided by B. So that set is also countably infinite. But all the real numbers, which we previewed earlier, are uncountably infinite. There is no way, it's been proved, there's no way to write a procedure that will eventually give you all the decimal numbers, including the infinite length decimal numbers. I don't want to go into that any further, but it's terrifying the first time you hear it, and beautiful. There are more infinities than those two, but we definitely won't go into that. So that was one thing just to blow your mind, right? So try and think about how you would count all the decimal numbers. Maybe I should tell you how you count the fractions. So the approximate answer for how you count the fractions is, imagine if it's A divided by B, imagine a two-dimensional plane with the A's and the B's, You just kind of go around like that. That's all I'm going to tell you. Okay. Russell's paradox.
That was hand waving.
Yeah, that was literally a hand waving explanation. Okay, so we already briefly mentioned the set theory that I gave you is completely, problematic because you can imagine in that set, I shouldn't have used the word set there. You can imagine a set in that collection of ideas. You can imagine a set which is, for example, the set of all sets, or the set of all infinite sets, or something like that. But you can also imagine the set of sets which do not contain themselves. And then you can ask yourself, does that set contain itself? And now you can't answer that question, and now you wish you hadn't asked it. Another very important concept, sorry, did someone have a comment about that? Another very important concept in programming is directed acyclic graphs, which are just directed graphs where you can never make a circuit, but they turn out really useful for lots of programming things. Matrix is like massively dependent on directed acyclic graphs because they're really good for kind of add-only data structure when there's synchronization happening between things on different parts of the world, and you can't communicate while they're happening, but later on you want to resolve them. So if you have a directed acyclic graph, you can just add bits onto it later. It's all fine. Yes.
Source control.
Yes, also well known from source control, including Git, and lots of other things. Directed acyclic graphs, really cool. Has anyone heard of the monster group?
Yes.
Yeah, it's on the slide. So the groups, the finite groups have been mostly classified into a fairly well-ordered set of, do I mean set? I don't know, group, collection, let's say, maybe it is a set of categories. I can't remember how many categories there are, but the weird thing is, so they're basically groups that work similar to each other. You know, so like we had D6, there are other groups that are like that, and they fit into one category. There's a few categories. Then there are 26 groups that don't really fit into the categories. One of them is the monster group, which I can't remember the size of it, but it's unimaginably huge and weird, and that's all I know. But it doesn't, you would have thought they'd all fit into neat categories, right? Even if there's a lot of them. How can something so simple as just the simplest possible idea of a well-behaved arithmetic throw out these things like the monster group? Also, anyone heard of the four-color theorem?
Yeah.
So the four-color theorem is actually a graph theory problem, even though it sounds like a maps problem. Because the point of four-color theorem is, can I colour in my map using only 4 felt tips without any countries touching each other which are the same colour? The answer is yes, but I'm not telling you how. And the way you do that is with countries are vertices, and the fact that a country touches another is an edge, yes?
Only because the globe is not a torus.
Yeah, so, okay, so I should have qualified that with a map on a 2-dimensional plane, not on a globe or a torus.
Are you pushing flat Earth theory then?
No comment on flat Earth theory, that's for a different talk.
You also ignore places like France, which have borders in 2 different places.
Yeah, so, okay, so I shouldn't have used the word country. Okay, so when reformulated as a graph theory problem, this is solvable because it's nice and well defined, because maths is better defined than Andy talking about maps. But yeah, so if each country is a vertex and the edge is the connections between them, the border between them, and you're on a 2-dimensional plane, so that works out in graph theory to be, you can draw it on a piece of paper and none of the lines cross each other.
But the Earth isn't flat. It's spherical.
No, that's why we've moved on. We've moved on from the Earth. We've moved on from the Earth. I can't remember whether on a globe it works or not. Certainly on some shapes.
Yeah.
Exceeds over, shoots a point and then.
Right, yeah. Okay, so yeah, on a globe it's fine, but on a torus you've got a problem. So don't move to a torus. Yes. So yeah, isn't it weird that you would expect that the fact that lines cross each other or not would be like, because we're in maths world, that wouldn't matter, but actually in a planar graph it does matter whether the lines cross on a 2D piece of paper. Yes.
I think it actually doesn't work anymore from maps. We make the assumption that countries are one whole thing and there's nothing mixing in or being part of a different country. And we have exclaves and enclaves, so I don't believe that maps can actually be drawn with this anymore.
Yeah, so the maths definitely does not map one-to-one to reality in this case. But yeah, so the weird thing about the four-colour theorem is that in order to prove it, we did a massive amount of computational work, which feels really weird, like it was a computer program checking thousands and thousands of cases. But if that troubles you, look up the five-colour theorem, which I talked about in a lightning talk last year, which I think is on YouTube. The five-colour theorem, which says you can colour in a map with 5 felt tips, is like fits on one piece of paper and is very beautiful. And that's all I've got to say. Thank you very much.